We are going to study about the topic moment of dipole. Now, first of all, how can we generate moment or torque in a dipole? Let us consider a dipole has been placed where the charges are placed at its two ends. Let two forces F1 and F2, which are oppositely directed, are applied at the two ends of the dipole. Now, if force F1 is equals to force F2, then there will be no translational motion, but torque will be generated. That is, the system will start rotating. So the dipole moment rotated due to the generation of torque. But how can we put a dipole in such a place that it can be rotated? So let us consider a uniform electric field, and a dipole has been placed within the electric field, making an angle theta. Now, equal and opposite forces F will be acting on the two ends of the dipole because both the end charges are same. One is plus Q, will be attracted towards the negative side, another is minus Q, will be attracted towards the positive side. So this is how we can generate torque within a dipole when placed within an electric field. Now, as the torque generated, the dipole will start rotating along this direction, along the direction of the arrow. The most important thing we have to take in mind that the electric field must be uniform. If not so, then translational motion may occur or will occur. But if the field is uniform, then there will be no translational motion and only rotational motion. Now, torque is equals to force into perpendicular distance. Now, as we know, force stands for charge into electric field, and the perpendicular distance has been measured as d. Now, now from the triangle A, B, and this point D, we can obtain the value of the length d as 2L sine theta. Placing them in the equation, we obtain the value of torque as E dot 2L dot Q sine theta, which later on in note has been mentioned as E dot P sine theta. Both E and P are in magnitude form. Later, we finally obtain torque equals to E cross P. I repeat, torque equals to E cross P. Now here we have two special cases, that is for theta equals to 0 and another is theta equals to 90 degree. Now if theta equals to 0, will there be any torque? I think no, because as we place theta equals to 0, sine theta stands for 0, so torque will be 0. And for theta equals to 90 degree, we are gonna get maximum value of torque as sine theta equals to 1. So now we are going to discuss about electric flux. As you can see, a plane A has been drawn. Now, as the electric field lines appear and passes through the plane, here the measure of electric flux begins. It is been defined as the lines of forces passing through an area which is normal to the surface. Why it has been mentioned like normal to the surface? If the surface is normal to the direction of the electric field lines, then maximum number of field lines will be passing through a surface. Let us consider this diagram and another set of diagram where the plane has been making an angle theta with respect to electric field lines. You can see here, as here the axis of the plane and the axis of the field are parallel, or we can say the plane is perpendicular to electric field lines, but here the plane makes an angle theta with respect to the direction of electric field. So when it is in same direction, the axis of the plane and the electric field, maximum number of lines passes, which is the measure of electric flux. And when the plane makes an angle theta, then lesser number of line passes. So we have to consider the component which is along the direction of the electric field. So when we measure flux for a small surface dA, maybe this blue surface can be considered as dA surface. Then we have to consider E dot dA cos theta, E product dA cos theta for the measure of flux d phi. Why E dA cos theta? This cos theta comes from the cos theta component or the term of the direction of the area or the direction of the field, whichever you consider. Next, there is a note that has been mentioned. Electric flux is positive when leaving the surface and is negative when entering, which is can be shown from this diagram. Like when this arrow is entering on this front side, it will be considered as negative, but on the back side, that is when the arrow is moving out, it will be considered as positive. Hence the total flux within this surface will be 0. Now next we come down to Gauss theorem. What is Gauss theorem? The total flux that will be enclosed by a charge containing body Q will be stated as Q divided by epsilon 0, where Q will be any charge body, and in general we are going to consider a spherical Gaussian surface which will completely enclose the body or the charge body. Hence, whatever may be the shape or size of the Gaussian surface, if it completely encloses the charged body, then total flux will be stated as phi equals to Q by epsilon naught. But how can we measure for any type of body rather than any uniform body, like for body with any shape? So to obtain the measurement of this, we have to study about a special angle which will be known as solid angle. Now as you can see here, a simple sphere has been drawn. Now here from the center of the sphere we have marked a small portion of sphere as dA, and the distance from the center to any part of the dA has been marked as r. As you can know, say it is a radial distance. Now what is solid angle? Solid angle is the angle obtained by the surface dA for the point at the center, or you can say this sphere is the spherical part is the solid angle. Now we come down to the formula of solid angle, which is area divided by r square. This area divided by r square. In differential form, it has been mentioned as dA cos theta by r square. Now we obtain the result for total solid angle. Total solid angle has been directly mentioned as 4 pi. It's very easy to find. If area of this sphere will be considered as 4 pi r square, where r square gets cancelled, and the total solid angle will be measured as 4 pi. Irrespective of all this, though solid angle is quite a big topic, only small part has been mentioned for the sake of the calculation and making Gauss theorem proved for any body, which will be obtained from the notes that has been provided. Now on, we are going to study about few applications of Gauss theorem, which will be few special cases, like the case study. First, we are going to consider about infinite long wire. So this is an infinitely charged long wire. We will consider here that long wire is positively charged. Okay, so if the wire is positively charged and having negligible thickness, only we consider the length of the wire. From that infinite part, we will consider an L length part of wire. Then the line charge density of that wire will be lambda equals to Q divided by L, which is defined by charge per unit length, is the line charge density. Now, as the straight wire is charged, all its electric field will be radially directed outward. Hence, the Gaussian surface forms the shape of a cylinder. It has been mentioned that top and bottom surface are neglected. Why neglected? This top and the bottom surface, which has been not shown here, will be neglected because here the direction of electric field, which is already in outward, and the direction of these planes are perpendicular. Hence, they will be neglected. They will not come into consideration for the calculation of electric flux or obtaining in the desired result we want. Now, what is the use of this? By using simply Gauss theorem, we will be easily calculate the electric field due to this infinite long wire, and the result obtained as E equals to lambda divided by 2 pi epsilon naught r. It has been easily calculated and shown in the notes. I wish you can follow it. Now, with this result, we come down to the second topic, that will be infinitely charged plane. What is that infinitely charged plane? As you can see, it has been mentioned a positively charged plate. So let us consider a piece of plate from an infinite sheet. It's a positively charged plate. Hence, the electric field lines will be directed outward from the plate, and right for both sides of the plate, like the side which is visible and the other side of the plate. For both the sides, the electric field direction will be pointing outward. So here we come down with surface charge density, which will be the ratio of charge divided by the area occupied by the surface. Now, as here are two surfaces, one for the front side, another for the back side, where electric fields are generated. So we are going to consider two Gaussian planes. Two Gaussian square planes will be considered for this. So keeping in mind that we obtain the result of electric field as E equals to sigma by 2 epsilon naught. The calculation can be followed from the notes. Next and final, we come with uniform charged sphere. So a uniform charged sphere which is positively charged with radius capital R has been placed. Now we consider a spherical Gaussian surface. But why spherical? It can be square, it can be cylindrical. But as you know, if we consider a spherical charged body, and if the direction of electric field is drawn, like for each and every point, it is bound to form a spherical shape. Hence, the Gaussian surface has been drawn in a spherical form. So, the Gaussian surface has been kept at a distance small r away from the center of the charged body. So, this encloses the charged body. Now, when we perform the calculation of the electric field due to this charged body using the Gaussian law, we obtain the form of equation of electric field in the form of sigma r square divided by epsilon naught r square. Keeping in mind that here the area that has been considered for the Gaussian surface will be used as surface area of sphere. Please see the calculation from the notes. Now, after seeing all the calculations, you will find that further for this uniform charge sphere case, it has been mentioned with three special cases. What are the three cases that can be explained from here? There can be a case, special cases for the uniform charge sphere. So as we have obtained the equation of electric field where the point lies at in on the space outside this sphere. So the first case stands and P point lies outside this spherical shell. So hence we are going to obtain the same result as we has obtained above, because earlier the Gaussian surface was such that it enclosed the charged surface. So hence the P point must be at such a distance away, which is r, and is greater than capital R from the charged sphere. Now the second point lies where P point lies on the spherical shell. Like this P point is now lying on the spherical shell. Hence, both small r and capital R will be same. So cancels out each other. Sigma by epsilon naught. Now, if P point lies inside the spherical shell, will any electric field be present? Yes or no? Just answer. The answer will be no. But why no field will be present? Let's see. Now, as per the diagram we have considered, if P point lies inside the charged sphere, it will seems as if this. The Gaussian surface now encloses a space which does not enclose any charged bodies, because all the charges lies outside surface of this sphere, and the Gaussian surface, this gray area Gaussian surface, is when no charge is present, hence no electric field will be present. Thank you. Read down the notes and the chapter ends here.